In this video we're going to talk about the pH scale, where it comes from, and what pH actually means. So when we're talking about pH, we're talking about solutions dissolved that are aqueous, or dissolved in water. And water itself actually has some acidic and basic properties. Water actually auto-ionizes, which means it breaks apart into the hydronium ion, which we know represents an acidic particle, and a hydroxide ion, which represents a basic particle. And that looks like this. So you have water molecules. One water will remove a hydrogen from another, and you'll end up with hydronium and hydroxide. So this happens, but it happens at a very, very low molarity, or low concentration. In fact, it happens where you have a concentration of 10 to the negative 7th molar. That's a decimal with 6 zeros and then a 1 after it. So very, very low concentration. And this is actually where our pH scale is based off of. When we say a pH of 7 is neutral, that comes from the fact that, well, its concentration of hydronium ion is 10 to the negative 7th. So how do we get that? Well, pH actually represents the negative log of our hydronium ion concentration. And all log means is 10 to the what power? So if we're looking at this, you can ignore the 1, because 1 times anything doesn't make a difference. 10 to the negative 7. If you took the log of 10 to the negative 7, you'd have negative 7. But since we have a negative in front of that, negative times negative 7 is positive 7. And that's where we get that the pH of neutral water would be 7. Right? There's a couple other things we're going to look at with this, and a couple other things we're going to quantify, but that's the basics for the pH scale comes from. Now, we also say it goes from 0 to 14, and I'll explain where we get that number. But first, let's take a look in general. You can see that the hydronium ion concentration times the hydroxide ion concentration gives us 10 to the negative 14. And we can see that right here. And that's a constant. That's actually called the equilibrium constant for water, 10 to the negative 14. And that doesn't change. Whether you have an acidic solution where you have a higher concentration of hydronium ion, or, actually, you know what? Go there. If we have a pH of 1, which is super acidic, you can still see that if you multiply this number by this number, you get 10 to the negative 14. So the fact that that's a constant means that those two variables have an inverse relationship to each other. As one of these increases, the other one goes down. And that all happens because if you have a ton of acid particles in there, and you have a base particle floating around, it's going to get consumed and neutralizing and converted back to water at a much higher rate. So, as one goes up, the other goes down, so they're inversely related. A couple other things you can also do. If we know the pH, we can determine our hydronium ion concentration. Since pH represents the negative log, or 10 to the what power, times the negative sign, of the hydronium ion, we can then say that going the other way, we're going to do the exact opposite. We're going to raise 10 to the negative pH in order to determine our hydronium ion. Now we can also analyze the solution based on its amount of basic properties, or its hydroxide ion concentration. So, to do that, we know that whenever you multiply the hydronium ion times the hydroxide ion, you get 10 to the negative 14. So, if you know one, you can figure out the other. All you would have to do is rearrange this equation to solve for the hydroxide ion. So you would divide 10 to the negative 14 by your hydronium ion concentration. But you could also determine the pOH. It's not as commonly used, but it's still something we can calculate, and we're going to need to calculate in this class. And that's going to be, similar to the pH, pOH is the negative log of your hydroxide ion concentration. And again, you can go backwards with that to find that our hydroxide ion concentration is equal to 10 to the negative pOH. So let's just do an example problem and see what this actually looks like. The other thing you need to know, is that the pH and the pOH have to add up to 14. Alright, so if we have a solution that has a pH of 2, and we need to determine the hydronium ion, hydroxide ion, and the pH of that solution, all we have to do is to find the hydronium ion, we go 10 to the negative pH. So since the pH is 2, that'll give us a value of 10 to the negative 2. The pOH, we said pH and pOH have to add up to 14, so you just take 14 and subtract the pH from it. Since the pH was 2, that gives you a value of 12. And then you can determine the hydroxide ion concentration by raising 10 to the negative pOH, and that would give you 10 to the negative 12. Another thing you can do to check your answer at the end of all of this is multiply your hydroxide ion concentration times your hydronium ion concentration, and that would give you a value of 10 to the negative 14. So that's how and we can check ourselves on this by adjusting the pH to 2 and seeing that our answer matches our prediction. So you can see that these values work. So our concentration of hydronium ion, 10 to the negative second. Hydroxide ion concentration, 10 to the negative 12. And our pH would have to be 12.